All right, well, welcome. In this video, we're going to be looking at Lesson 2.2, and we're going to be looking at what we call linear models. Now, you've done things before with linear equations. Now, a linear model just means that we're going to be working with data, and sometimes data doesn't fit exactly to a perfectly straight line. And so we refer to it as a model because we're going to model a line to fit the data as best as we can. Now, one of the most common equations that we're going to be dealing with is a linear function. Remember, that's in the form y equals mx plus b. Now, that's what we call slope-intercept form. There's another form that we'll be talking about in just a second that you want to also be aware of. But y equals mx plus b is one you've seen so often, you should already have that memorized. But if not, that is one that you really need to know. All right, let's look at this data. So we're going to be working with this data in this lesson. So this is talking about some data with the carat weight of diamonds. And so if you read that paragraph, it says, jewelers emphasize that the price of a diamond is determined by the cut, the carat weight, color, and clarity. The table gives the carat weights and approximate prices in US dollars for 20 diamond rings. The data are graphed below. All right, so if you look at some of these weights, you can see that they have a couple of different weights here that are the same value as far as the weight of the diamond, but the price of the diamond is different. And so let's see if we can find a couple of those quickly. Like, for example, here we have one that's 0.17. Here's another one that's 0.17. So those two, this one here is a $517.50 diamond. This one's $529.50. And the reason why in that price difference, like the paragraph said, is they're valued based on not just their weight, but also the color and clarity. And so you might have that slightly more expensive one, might have a little less flaws, might be a little bit clearer. So that's why that one might be a little bit more expensive. And then what they did is they fit that data, all of those different weights and their price, to a scatter plot. So you can see that those lines in that scatter plot, or those points in that scatter plot, fit pretty closely with the line that they have graphed there. So a linear equation would be a good equation to use to model this data. So let's look at some ways that we can come up with that linear equation. So some things that we want to make sure that you know. That's, first off, let's look at this, what's in red there. You want to make sure you know the point-slope form in addition to the slope-intercept form. So the point-slope form is this: y minus y1 equals m times x minus x1. You might want to circle the y1, the m, and the x1, or highlight it, or use a different color pen. The reason for that is because y1, m, and x1 are all going to be replaced by numbers. And if we don't have the slope over here on the left, if we don't have the slope, we're going to need to know the slope formula. So the slope formula, remember, is the change in y over the change in x. So y2 minus y1 over x2 minus x1. So for this one, it says, find the equation of a line going through those 2 points, which relates the weight and the price. So we're going to use these two coordinates. So again, we want to put this in point-slope form, but they don't tell me the slope between those 2 points. So we need to figure out what that slope would be first. So using that slope formula, we would take the 1400 minus the 600 and divide that by the x2 minus x1. So 0.32 minus 0.18. Now when you do that, you're going to get 800 divided by 0.14. But we can do that in our calculator, and we're going to get 5,714. And then we'll just round this nearest hundredths, so we get 0.29 there, and round that to the nearest hundredths. So that's going to be our slope. Well, now we're going to pick one of those points. It does not matter which coordinate we use. We can use either one. So maybe you decide, well, you know what, this 0.18 and the 600 look a little bit smaller than the 0.32 and 1400, so I'm going to use that one. Really, it doesn't matter. So we're going to use this as our x1 and then this as our y1, and we have our slope as the 5,714. So we would take y minus my y1, which is 600, equals my slope, which is 5,714.29, times x minus my x1, which is 0.18. We could simplify that. I'm going to simplify that by distributing the 5,714 through. And when we multiply 5714.29 times 0.18, we get 1,028.57 approximately. So now I would add 600 to both sides. I wouldn't add it to the x. I'd add it down there to that negative 1,028.57. And we would get our equation then being where y equals 5,000. Oops. It's supposed to be a 7 there. $5,714.29, or 5,014.29x. And then this would be minus 428.57. That's our equation that we could use to model that problem. Now, again, the reason why I say it models a problem is because it doesn't fit those points perfectly, but it's going to come pretty close. Now, let's use this to answer the questions here. It says in part B, interpret the slope of the line in the context of the problem. So I'm not going to write all this down. So the slope of the line is this piece here, remember. So what that means is that's each caret. So the 5,714.29 represents an increase by about that much dollars. So it'll be about $5,714.29 increase per caret increase. So for every caret increase, so going from 1 caret to 2 carats and so on, the value is going to increase by that much. So if you're ever not sure, well, how do I figure that out? Well, remember, our slope is y2, or our change in y over our change in x. Our y values, the $1,400 and the $600, that was the cost. And the x's, were the 0.18 and the 0.32, that was the weight of the caret, or weight to the diamond, caret weight to the diamond. So you can think of it as a cost per weight. So that $5,714.29 represents the cost per caret weight, is another way to reference it. All right, so let's use the model to estimate the price of a 0.3 carat diamond ring. So x, remember, represents the carat weight to the diamond. So all we're going to do is we're going to put 0.3 in for x. So when we do that, we would set it up like this. And when you just plug this in your calculator, when you plug that in your calculator, you'd get your answer of $1,285.71. So that would be our estimate for a 0.3, so a 1/3 carat diamond ring. Now it says, why is this model not good for predicting the cost of a 0.05 carat diamond ring? Well, the reason why is if you put 0.05 in for x, so that'd be like a small little shaving of a carat, of a diamond there. But if we were to put 0.05 in for x, here's what we would have. And when you go and type this in your calculator, you'd end up getting negative $142.86. So in the context of this problem, a 0.05 carat ring wouldn't cost you anything. You'd actually get paid $142.86. That's what that represents. The cost to you would be a negative 142.86, meaning you get paid that much. Okay, so that does not make any sense. So for this model, it's maybe a good model for some of the values, but it's not going to be a good model for a really small value, a really small carat weight diamond. And then it says in part E, why is a set of data not a function? Now remember we said in the previous video that a function is where each input has exactly one output. So you would have no repeats. Like if you look down a table of values and if you see that you ever have any values for x that repeat, you want to look at the values for y. And if they're different numbers, that's how you could tell it's not a function. So this is not a function because it'd be like putting 0.17 into a machine and getting your M&Ms and putting 0.17 into the same machine, and now you get your Snickers bar. You get two different outcomes for the same input, and you don't want that. So this is not a function. So it's not a function. I guess it didn't ask if it was or wasn't, but the reason why it's not a function is you have two different inputs, or two inputs with different outputs. All right. I want you guys to take a minute, and I want you to use that equation that we talked about earlier. So the y minus y1 equals m times x minus x1. I want you to use that formula. Remember, you might have to use the formula for the slope, which remember is a change in y over the change in x. And I want you to find an equation of a line going through these two coordinates. So I want you guys to go ahead and pause the video and work this one out to find the equation in slope-intercept form, and hit play when you're ready to check to see if you've got it correct. All right, so you should have gotten this equation that's circled there. So if you didn't get that, let's check where you might have made a mistake. So first off, what's in green is where you're going to use your slope. And so you should have gotten negative 0.01 as your slope. If you didn't get that, double check your work, make sure you have it set up right, make sure you subtract it in the right order, and so on. All right, so then the purple there is how we'd set that up, then using that point slope formula. And so when you go and distribute, oh, by the way, too, if you notice, I used the 2004 and the 9.8, and I did that on purpose because I'm guessing most of you guys use 1972 and 10.15, maybe because 1972 might be smaller. But if you didn't, either way, you should see that you get the same answer if you do your math correctly. All right, the last thing we need to talk about is this idea of, or one of the last things we need to talk about is this idea of interpolation and extrapolation. Okay, these are two brand new terms that you've never seen before, so please make sure you get this in your notes. Now, if you see the prefix there in interpolation, you see inter, and if you look at the prefix in extrapolation, you see extra. So if you think of the term or the prefix inter just means inside of, and extra means extra, it's outside of. And so interpolation is any time that we're making a prediction between known values, that's called interpolation. Where if you're making a prediction that's outside of any known values, it's called extrapolation. So let's think of it in terms of the rings that we were talking about earlier. So let me go up here. So in this table here, it looks like the smallest value in the table is 0.12. Am I right? Let's see, do I find anything smaller than 0.12? I don't think I see anything smaller than 0.12. And the largest value looks like it's 0.35. So if I were to use my formula, okay, if I were to use that model that we came up with, and if I used any number between 0.12 and 0.35, that's an example of interpolation, even if it's not in the table. Okay, so if I use a number that's not on this table, like 0.22, I don't see a 0.22 off the top of my head, I don't see it on there in the list. But so if I use 0.22 as my input, even though it's not in the table, it's between 0.12 and 0.35. So 0.22, if we use that as our caret weight, that's an example of interpolation. Now, if I were to use a value for my caret weight that's bigger than 0.35, like 0.4, or even the 0.05, that would be extrapolation, because now we're working with a number that's outside of any of the values that were in our table. So that's what we call extrapolation. So if you're working outside of the biggest and smallest numbers, it's extrapolation. If you're working with a number inside of our smallest and biggest numbers, it's interpolation. Okay, so make sure you get that down. And then the next thing that we need to talk about is this idea of a residual. So you have the observed values. Observed values are the values that we actually have from a table or that we've collected. They're actual data that we've collected. Predicted values, those are the values we get from an equation. So to find what we call the residual, we're always going to take the observed minus the predicted. The observed, the numbers that we have actually in our table, minus the predicted, the numbers we get from an equation. And the difference between those two will be our residual. Now it's okay, sometimes those values are going to be positive, sometimes they're going to be negative. So if the observed value is bigger than our predicted value, it'll be a positive number. But if the predicted value is bigger than what actually happened, then you're going to end up with a negative number. Okay, so let's look at an example. So here they tell us that a 0.16 carat diamond ring sold for $507. That's an observed value. That actually happened. So we're going to use the formula to find out what it would be for the model, and then we're going to use that to figure out what the residual would be. So the formula we're going to use is that same one, that we came up with on the front side, the $5,714 one. So let me just rewrite that equation. So we had y equals $5,714.29 times x minus $428.57. Okay, so that's the equation that we came up with first. And so they're saying that, well, what would be the residual for a 0.16 carat diamond ring? So we're going to put, I'm going to just erase this x. We're going to put 0.16 in there for x. So if we were to plug that in your calculator, when you do that, we would end up getting $485.71. Meaning we would have predicted that that diamond would have sold for about $486. But it actually sold for $507. So remember, to find the residual, we're going to take the observed, what actually happened, minus the predicted, the $485.71, and find that difference. And when you do that, we get a positive $21.29. So that means it sold for about $21 more than what we expected, is how we can interpret that. Okay, now I want you guys to find the residual for a 0.33 carat weight diamond. So again, I give you the observed right here. So if you don't have that table in front of you, the actual 0.33 carat weight diamond sold for a little over $1,400. So you want to figure out what would be the predicted value, and then use that to find the residual. So go ahead and pause the video and hit play when you're ready to check to see if you have the correct answer. All right, so how did you do? You should have gotten, for the predicted value, you should have gotten $1,457.14. And so again, you take the observed value, what that diamond actually sold for, subtract from it what you predicted it would sell for, and that gives you the residual. So this time our residual ends up being a negative number, negative $39.64. Or we could, these are all just, again, we're just dealing with estimates, so we could round this. So we could say it's about a $40 difference. And so we can say that it's sold for, since it's negative, it's sold for $40 less than what we expected it would sell for. That's the purpose of a residual. All right. Now if you remember from the last chapter, we dealt with finding the variance, then the standard deviations. We had that big table of values that we had to find when we were doing it by hand. Well, here we can find the sum of the squared residuals. They just refer to this again. But remember, that if we were to take each of the observed values and the predicted values, that's what we call the sum of the squared residuals. Okay, or I guess if we square each of those values and add them together, that gives you the sum of the squared residuals. And so we can use the sum of the squared residuals to see how close of a better fit we would have with the data. So if you're comparing two sets of data, whichever one with the smaller sum of the squared residuals has the best line of best fit for the data. So that's how you can compare two different graphs. Is the one with the smaller sum of the squared residuals is going to be the one that's going to be closer fit to the data. So that's the last piece you need to know. All right. Well, that's it. Hopefully, like I said, this made sense to you, and hopefully you took really good notes. Otherwise, if there's anything here that didn't make sense to you or it's something that you struggled with, remember to bring those questions to class with you tomorrow. And with that, I will see you then.